Assalamualaikum and hi, my name is Nur Atira binti Zahuri.
And I'm Nadiatul Hanan binti Haizan. So today we are going to present on
Magnetic force microscopy.
here is the table of content for our slides.
In this table of content, we have introduction, next basic concept, basic principle, methodology.
We also have interpretation of result, conclusion and application of MFM. Now let's focus on the slide of introduction to magnetic force microscopy, which is known as MFM. Okay, first of all, what is the magnetic force microscopy? The magnetic force microscopy is known as magnetic techniques for studying and analyzing both scientific and technologically magnetic phenomena in surface structure at micro and nano scales. Bear in our minds that the development of MFM is derived from atomic force microscopy, which is known as AFM. This is because the method makes use of a magnetic probe that is brought close to a sample and interacts with a magnetic strip field near the surface. Next, the vertical motion of the tip as it scans across the sample is determined by strength of local magnostatic interaction. And lastly, in 1987, after the invention of AFM by Martin and Wickramasinghe, MFM was introduced because the technique that offers high imaging resolution because it doesn't need a special sample preparation or environmental condition. Okay, let's move on to the next slide where I would like to explain in general about the basic concept of MFM. Okay, first thing first, we should know that there are two forces acting on the tip during the MFM measurements, which is first is magnetic force, second is van der Waals force. Next, the dominating force depends on the distance between the tip and the sample surface as the interatomic magnetic force persists for greater tip to sample separations than the van der Waals forces. Next, the image will be predominantly topographic if the tip is close to the surface. This region where standard non-contact AFM is operated. In addition, by increasing the separation between the tip and the sample, magnetic effects will become more apparent. And lastly, one way to separate magnetic from topographic effect is by collecting a series of images at different tip height. In this slide, we can see the example of picture on how the MFM works. And the last part that I would like to explain is about the basic principles of MFM. The first basic principles of MFM is the magnetic straight field above a very flat sample is detected by placing a small magnetic element, the tip, mounted on a cantilever spring close to the surface of sample. From the picture shown in this slide, we can see there is a cantilever, a specimen, and a detector where the detector will process the data in a computer and the magnetic element. Next, typical dimensions. The first typical dimension is cantilever length, which is 200 micrometer, tip length, which is 4 micrometer, the diameter, which is 50 nanometer, and the distance from the surface is 30 nanometer. Next, the basic principle of MFM is the force on the magnetic tip is detected by measuring the displacement of the end of the cantilever. Next, the forces measured in MFM application are 30 pn, which typical cantilever deflections in the order of nanometers. In addition, the force on the magnetic tip is detected by measuring displacement of the end of the cantilever. And lastly, The image of magnetic strip field can be obtained by slowly scanning the cantilever over the sample surface.
Next, I will explain on the methodology for our experiment. The test sample that we use for this experiment is magnetoferritin molecules. Magnetic force microscopy, or known as MFM, is used to demonstrate the production of magnetoferritin from apoferritin. As we know, ferritin is made up of 24 subunits that self-assemble in a cage-like structure and is used as spherical protein to ensure the magnetic iron nanoparticles is stabilized. This can be seen in this figure here. Both the inner and outer diameter are 8 nanometer and also 12 nanometer. Typically, these proteins can be found in a diversity of organisms ranging from prokaryotes to mammals, where the ferritin is distinguished by high thermal stability, which allows easy purification. Other than that, as we can see here, figure A shows the topography image, while figure B here shows the bimodal phase image. Hypoferritin and gold nanoparticles, which is 10 nanometer in diameter, show almost no contrast, whereas ferritin appears as a bright spot due to the magnetic interaction between the molecule and the cobalt-coated cantilever. As we can see here, ferritin molecules are located in the red circle shape here, while the gold nanoparticles is shown in the black colored circle here. The apoferritin molecules that appears as a bright spot is shown in the blue colored circle here. In this study, ferritin is used as the test sample because it has the ability to stabilize the magnetic iron nanoparticles during the imaging process using two-pass technique. As we can see, the two-pass technique is shown in the figure. Generally, the first phase of imaging is carried out by AFM, which is atomic force microscopy. This is to obtain the topography images. We also need to identify the dimension and the shape of the molecules, which involves mounting the sample and moving the AFM tip across its surface. Next, the second pass is then performed along the topography marked during the first pass that enables us to identify 4 magnetoferritin molecules. This process is known as MFM phase. Both AFM and MFM have been used to verify the effectiveness of the whole process. The first step of our experiment is we have to analyze the shape and dimension of magnetoferritin molecules by using AFM topographical images. As we can see here in figure A, this is the observation for their shape. The magnetoferritin molecules are clearly visible. It is observed that the molecules appear as circular shapes that are brighter than the substrate. As you can see here, all these circular shapes that are brighter are the magnetoferritin molecules, and the area of topography has a measurement of 3 times 3 micrometers square. Whereas for this figure B, this shows the observation for the dimension. As we can observe here, the height of different magnetoferritin molecules on random selected areas is measured, and the diameter obtained is 11 plus minus 3 nanometer. The statistics of both the frequency here and the height are clearly shown in this figure B. In this experiment, the bare analysis of the height of molecules achieved using AFM topographical method does not give us to distinguish certainly between magnetoferritin and apoferritin. Their diameters are measured as 10 nanometer and 12 nanometer respectively. This is because the existence of buffer residuals on the substrate that makes it less accurate to evaluate the height of the molecules. After analyze, now we will look at the interpretation of result. In this slide, Figure 1 illustrates the MFM characterization of magnetoferrite molecules on a selected area that has been performed several times repeatedly. We use different values of leaf height that are in the range of 15 until 100 nanometer. In Figure 1 shown here, we can observe that the topography of an area with size 2 times 2 micrometers square is obtained where magnetoferrite molecules are visible. All the bright spots here are known as the magnetoferrite molecules. Next, in Figure B here, it shows the standard phase image during the first pass in the tapping mode. In Figure C, it shows the MFM phase image in the second pass tapping mode. Here is the Figure C. Next, in Figure D shown here, we can observe that 4 magnetoferrite molecules are visible in an area of 800 times 800 nanometers square. As we can see here, we have 1, 2, 3, and 4 magnetoferrite molecules. Next, in Figure E here, it shows the tapping mode phase image, and lastly for in Figure F, it shows the MFM phase image. Now, let us discuss on the results that we obtained. In Figure A, it is estimated that the curvature radius of the coated tip is about 110 to 280 nanometer. This is because of the convolution effect with the tip shape that makes the lateral dimensions appear wider than the real ones. The estimated values are then compared with the values that is obtained when using SEM, scanning electron microscopy, coupled with energy dispersive X-ray EDX spectroscopy and mapping to image the tips used. After that, the values are obtained are a few hundreds of nanometers. In Figure B, the standard phase image does not allow us to distinguish between the molecules and substrate, although the topography shows a relevant contrast in correspondence of the magnetoferrite molecules. Why does this happen? This is because such contrast reflects variations in the energy dissipation during a cycle of tapping. As we know, AFM feedback loop maintains the cantilever oscillation amplitude constantly during the tapping mode. Thus, that is why the contrast in this figure may suggest the presence on the substrate around the molecules of residuals of apoferritin. The next figure is Figure C. This shows the MFM phase image acquired with 50 nanometer shows a clear contrast in correspondence of the magnetoferrite molecules. This clearly indicates the presence of magnetic material in the core of the molecules. Hence, we can conclude that the MFM phase image confirms the existence of a magnetic core in the molecules. As we know, we can achieve the objective of the study where we already confirmed that MFM confirms the production of magnetoferrite from apoferritin. Last but not least, we come to our conclusion for this experiment. From this experiment, we can conclude that ferritin is a protein that is made up of various molecules, including the magnetoferrite molecules that has been used as the test sample. In this experiment, atomic force microscopy, or known as AFM, was first used to map out the sample surface and then highlight the topography of the molecule, hence giving a general appearance of the molecule. However, AFM is not able to identify the magnetic fields of the molecule. Hence, by using a magnetized tape during the second pass in the MFM phase, this allows us to identify for the areas in the molecule. Therefore, both techniques of AFM and FMM greatly contribute to the understand the molecule in detail, where the dimensions of the molecule are based on AFM, while the presence of the magnetic molecules are based on MFM. As we know, MFM has been used as the preferred technique by researchers globally to study the magnetic properties of numerous biological molecules in various organisms, from bacteria to mammals, because it brings many benefits such as being non-destructive when studying biological components, besides providing high resolution. Last but not least, here is the application of MFM for studying nanoparticles. As we know, nanoparticles are nanoscale particles, where it means that the particles are ranging in between 1 to 100 nanometers in size. This means they are very small to be clearly seen by the naked eye and also under the light microscope. Hence, by the help of magnetic force microscope, it has become possible to observe and study a wide range of nanoparticles. One of the biggest advantages of MFM technique is that it can be used in a wide variety of conditions, including in varying temperatures, liquid conditions, as well as vacuums. Therefore, this makes it an excellent technique to study various nanoparticles in their respective environments. As you can see in this figure, there are two types of nanoparticles that are organic and also inorganic. For organic nanoparticles, it consists of polymeric nanosphere, polymeric nanocapsule, polymeric micelle, liposome, and also dendrimer. Whereas for inorganic nanoparticles, we have mesoporous silica nanoparticle, carbon nanotube, iron oxide nanoparticle, gold nanoparticle, and also quantum dot. That is all from us. We hope you enjoy our video.
Thank you and
Bye.
bye.